You guys ready? Sorry I'm late. My CS2 class had a test. And it always seems to run over, no matter how short it is. Okay. Question 1 of the first review sheet. All we're doing is a subtraction, right? We're subtracting EVX from EAX. So what should EAX then contain? Oh, very good idea. Send you to college. Oh man, this thing's loud as heck. It's like blast your eardrums. Is that better? Okay, so here we load the registers with those values. Now we're just subtracting from EAX. So EAX should be what? 10. EVX is going to be the same as it was, right? 10. We didn't mess with the other registers, so they would be 17 in it, right? Yes.
I know I'm skipping ahead a little bit, but this has already been posted. But you haven't posted anything about memory at all.
All right.
So, what's the question about that?
Okay. I thought I put up the slides.
Well, the slides, that's probably this the slide.
Let me grab the slides and I'll tell you based on that. I didn't do that. I'll be glad to put up a memory review tonight, but for right now, I'll just show you what's gonna be there, okay? So let me go ahead and grab the memory slides. If I can find them. So are you guys okay with those registers and stuff? Are you good with all that? And I made sure I gave the answers, so if you're working down, you should just be able to compare with the answers there. That's at least half your test. So if you can do that, you have 50 points right. That's actually going to be like 75% of your test. Now, what I'm probably going to do is ask you 5 questions off of study sheet 1, 5 questions off of study sheet 2, 5 questions off of study sheet 3. How long would it take you to do like a minute, 2 minutes?
5 minutes.
Like an hour and a half straight off before no one.
That's fine. I could have never thought
I
of that.
5 minutes, 5 minutes.
So are they like a couple of minutes per problem? Is that fair enough?
Yeah.
So if I ask you 6, 6, and 6, that's 18. That's about 36 minutes. Okay. Oh, good. This review will be easy. Okay. Of course, I told you about twice.
One question, when you do number 2 on your review sheet, you just please?
Which review sheet?
Yes, your first one. Number 2, you're just on it.
Okay, sure. So here we go. There are your registers. And we subtract EAX from EVX. So, let's see, 29 minus 16, so it should be what, 13 or so? Yeah. EVX should be 13. EAX should be, I should have given you those answers, right? Yeah. So, is there some specific question you have, Brandon, on that? I'll be glad to. You got time? By the way, I actually wrote a program to create these study sheets. Randomly created those values. Okay, so you're not impressed. That's fine.
That's cool.
Would you use to make C++?
I used C# because it was just a lot easier. C++ would have been almost as easy. So I use C#, but C++, yes.
How do you read your problem? You said, so does it
So you're subtracting EAX from EDX.
Alright, so yeah, subtract, yeah.
Right, so it'll be 29 minus 16, and then the result should be EBX is left with 13, and nothing changes in EAX, it'll be the same value.
Alright,
Okay,
okay, alright.
so any other questions?
No,
If
Yes,
we
sir.
put the computer scroll just a little bit toward the center.
Scroll down,
Up.
up,
Yeah, so
Sure.
let's say we changed EAX, EDX, and we're given a negative number. Would that be first, would it run? And if we were given a negative,
it will absolutely run, it will be a negative number, so let's see,
like we would have to store it as a,
yeah, so let's see, 16 minus 29, what would that turn out to be? Negative 13, that could be stored as a 2's complement in the register. It'd be negative 13, but it would, if you look at binary, it would look like a 2's complement.
like from our first test kind of.
Correct, exactly.
Okay, excellent. I thought it would be like an extra bit or something or just happened.
No, it would definitely be a 2's complement. Yes, sir.
Did you do 1 or 2 from the report 2 and report 3?
Be glad to. I'll do whatever makes you guys feel comfortable, because I want to make sure that we're on track here, and I don't like the idea that I have left these things unexplained. Here's part 2. And I believe, okay, so now we move a value to EDX. And we could have just pushed 15, but I wanted to make it really clear that we're pushing a 32-bit value. And remember, 32 bits is the same as 4 bytes, right? So you push 15, you push 26, and you call my function. Here's my function. Set up the stack frame, push EDX. Now, the first one, that's the first one that's pushed. That's the second one that's pushed. It doesn't matter which order you do this. You could do it like this, and it will be okay. You still get the same answer. Okay? You'll see the first number that was pushed was what? 15. Okay. And I made a mistake here. My program is. I think all the subtraction problem. Okay, so let me change the problem. I'm joke. It's not a joke. I think I made a mistake. The first one. Okay, so I'll repost this after I fix this.
Well, no, you changed it, so.
What now?
It was right. But you-
So was it right?
Because you flipped it originally.
Okay.
Flipped it into it again.
Yeah, no. Okay. All right, so now we get 11. Problem number 2. We're pushing 19 first, 54 second, call my function. We pop the numbers, we get them up, we multiply the numbers, 54 and 19, so we multiply this together, we get 1,026. Whatever that turns out. So. Yes.
I'm sorry, I feel like, could you go a little bit and just went like a little too fast?
Yeah.
Push 1954, so EAX is 19, EDX is 4, and you go down to my function, you just hold it,
Yes.
and then take,
So it doesn't matter which of these you actually, this was actually random, what register it went into. In fact, I had the program just pick registers from random. And so it did an IMUL, EAX, EDX, just multiply the numbers together.
one question, you change this sheet, because after writing it,
Yeah, I noticed a couple of mistakes and I changed a few things, so the later sheet is the one you should follow.
Is it alright if we can just like walk through one of those questions?
You know what would be really cool is if we could just go ahead and run Visual Studio on the laptop.
That too.
That's nice. All right, so I don't have my laptop, but let's go ahead and create it in my favorite editor called Notepad. Oh, of course, these freaking computer locked down, so you can't do that, you gotta. Okay, so what kind of problems do you want me to do?
That one that we were just working on.
Okay, let's go ahead and we'll make up our own. Change this font. Okay, so let's say, EDX, comma, 12, push, EDX, okay, so far so good? First number we pushed is, 12. Push, move. ECX, comma, 14, push, EDX, excuse me, ECX. So far so good? Now, when I push those two values, how many bytes did the stack pointer change? 4 and 4, right? So it changed a total of 8. Okay? Now I'm going to call my function. Now I'm cleaning up the stack pointer here, but here's my function. Let me go ahead and bail out of here so then it's still go. Bail out here. All right, now my function is going to set up the stack frame. First, we're only preserving EBP. What's the point of that? Pushing EBP to preserve it so we can get it back later. Okay. Because remember, this isn't like in C. You know how in C you can use a variable all you want. No matter these registers, you can't just trash them and then expect everything to work. So what we have to do is preserve it first. So we push it on the stack so it's preserved. Now we're going to use EBP to access everything on the stack. So we're going to move the stack pointer into that. So now EBP is the same as the stack pointer, okay? So we can use EBP now to get stuff off the stack, just as if it was the stack pointer. Okay, do you want to add, subtract, multiply, or divide? Move EAX, and you want to move, so I'm going to give you a choice here, since you're helping me make this problem. We can either use the first parameter or the second parameter. Your choice. Okay, the second one is push is +8. You wait. So now we're going to move. Wow, what are you typing in the darkness here? The first parameter that was pushed is +12. And what if I'd have pushed 3 things instead of 2? I pushed 2 registers. What if I'd have pushed 3? It would have been 8, 12, and 16. What if I'd have pushed 4? It would have been 8, 12, 16, and 20. Okay, so you can push as many as you want, and it just continually changes the stack point. Okay, I do EAX, EBX, and divided. And the interest, oops, comments there. Divide is that EAX is integer division, just like you do in C, you know, integer division. In this case, let's see, we're dividing. So it's, yeah, but in EDX it's going to be the modulus, right? And that's how they do modulus underneath the covers. You know, the C modulus operator. Well, it's a byproduct of division. Okay, so we divided. Let's see, we got EAX is the second one we pushed. So EAX is 14, right? EBX is 12. So we actually, integer division, we're gonna get 1, correct? Shouldn't we get 1 at this point? Okay, so EX. Now, restore the stack pointer, and I'm gonna point out it's sort of a problem in just a minute. Pop EBP return. Now, that's a C++ return. What if what if I was counting on that to be a certain value? Would this be a problem if I didn't count on it to be a certain value? Maybe. EAX is always a return value, so you know that's going to get closed up. So just to make sure, let's preserve. This isn't mandatory. You might not have to do this. It depends on your code. Preserve EDX, and restore it here. Now, did you notice I'm doing this in reverse order? Push EBP, push EBX, and you got to pop them in the reverse order. Yes, sir.
So you're adding the stack pointer value and EAX.
You're adding what's in the stack pointer. These see these little brackets? You know in C you have the little asterisk that means the contents of the pointer? This means the contents of where it's pointing to. So you're not adding the actual value of the stack pointer, but you're adding what it's pointing to.
So it's pointing, what is the value of where it's pointing? How do we know that?
Okay, good question. So what we did was we said, okay, let's take the stack pointer. And we'll make sure the EBP is going to contain whatever the stack pointer points to. And that's how we know. And when we're pushing stuff, we push the first parameter, we push the second parameter, the instruction pointer gets pushed, and EBP gets pushed. So you know you can count on those values as the stack pointer gets adjusted. Okay?
In this case, the first parameter would be 12.
Plus 12. The second parameter is plus 8. And if you push more parameters, it would just be plus 8, plus 12, plus 16. And those are, if you push parameters that were only 2 bytes, say AX or a word or something, it would be plus 8, plus 10, plus 12. If you push bytes, it would be plus 8, plus 9, plus 10, plus 11. It just depends on the data size. Okay? So here, preserve that, and when you restore them, you got to restore them in the opposite order. Okay? So, let us go to C++. Man, I don't have C++ to show. Yes.
In this particular example, what is EBP
Okay. So the first one I pushed is going to be EBP plus 12, and it will actually have a value of 12. The second one I pushed is going to be EBP plus 8, so I'll have a value of 14. Okay. I'm going to do another one. Let's see what we got.
One of the packets so we can actually see the targets.
June? I'm sorry, what, Brandon?
I was saying you want to out of the packet so we actually can like follow along and if you have that correct.
Yeah, I was actually doing that, and someone asked me to do one, make one up, and I did. I'm glad to do that. Yes.
So we will have to make up one of our own.
Pardon me?
We have to make up one of our own.
That's a very good idea. I'm glad you suggested that.
I didn't suggest it. I'm just saying. What's up with you guys? No, let's confirm it. Because if we do.
Yeah, I would probably ask you to write one, and I'll probably say push 2 integer values and add.
Can you go over it one more time?
I'm glad to. I'm here for you guys to do whatever you want. I'm going to do tonight, except I won't stand on my head. I will listen to you. Might find that hilarious. Okay. Let's find. How about this? Problem 4. Okay. The first number we're going to push is 30. The second one is 12, right? Now, so this will turn out to be BP plus 12, right? And this one will turn out to be BP plus 8.
And it's 12 and 8 because those are the bytes.
Because when we push, that's how many bytes we're adjusting the stack by. Now, let me give you a caveat, and I'm not trying to confuse you, but let me just give you a caveat. If I push stuff before this, like I said, move EBX, 44, and push EEX, and that would be BP plus 16. Ah, crap. That's left. Wait. Okay, so that's the caveat, that the more you push, the more the stack pointer gets adjusted, and then the further away it's gonna be, see? So you could actually push 100, but all you would have to do is realize that you just have to adjust for that, okay?
Okay, so essentially VP plus 12 is like a representation, like a pointer, how you said.
Exactly,
Okay.
it's just like a C pointer into that thing that you pushed onto the stack.
Okay.
And the most recent one always starts at +8.
Your first parameter, whether it's a byte, a char, or whatever, it's always gonna be +8, yes. And then after that, you just sort of count, do the math after that, and just figure out, how much you pushed. So, for instance, and I'm not trying to confuse you, I just want to be clear on all this. If, let's say, I did that. Now, he's still going to be BP plus 16, because he's relying on everybody that comes before him, okay? But now, if I push this, see, he's relying on what comes before him, okay? So this would be BP plus 8. This difference between, it's actually BP, okay. Surprised you guys said less than that. Yeah, because the one that came before me was only 2 bytes. Okay, that's why, you see, because, I'm sorry for looking at this so fast. This one is 2 bytes, because remember VX is only a 16-bit register. Since it's only 2 bytes, then we're only going to adjust the stack pointer by 2 bytes. Okay, so that means the next guy up the line, it's only an extra 2, not an extra 4 like we've been doing. So it's all just math as far as, it's all relative from where you came from. That's kind of like your life or my life. It's all relative to where you came from, grasshopper. Okay, let me get rid of all this crap here so we can sort of get back. And what I did was I tried really hard just to limit this to 2 parameters pushed, and that's what I'm doing the best. I'm just relying only on 2 parameters, and I'm trying to keep everything real consistent. So you get that. If you get that, I'm going to be thrilled if you can just get that. Okay, we're not trying to become, assembly language programming experts. We're just trying to sort of get the sort of concepts across. So I'll be thrilled if you guys can do this. Absolutely. Okay, so here we go. We pushed 30, we pushed 12. Now we called our function. We got the first one off the stack. We got the second one off the stack, and we multiplied. Okay? And by multiplying those 2 numbers, notice this is kind of messed up. Preserve EBP, preserve EDX, restore EDX, restore EDP. Now, why is it, and I mentioned this a couple times, why is it I'm not going to preserve and restore EAX? Because that's what's returned. And everybody who programs assembly knows that when you call a function that returns something, EAX is going to contain the return value. So you can't say, well, I was using EAX, why'd you mess it up? So it's just understood that EAX does not need to be preserved unless you know what you're doing, unless it's part of your old system. You can decide to do that, but in most cases, the return value is going to be in EAX. It's kind of like C programming. I can give you general guidelines, but it's not going to always be the truth. It's not always going to be the way it is. I've had assembly functions where I had to preserve EAX, but those were functions where I didn't return a value, maybe a void. C could have a void that doesn't return a value, and if that's the case, then maybe you would preserve EAX. Okay, so I can't give you a hard fast rule that you never have to, because sometimes you might. Yes.
So when you're moving into EAX right there, EBP plus 8, wouldn't EBP, the value of EBP be 20 because you pushed 2 more times or above that?
Let me see. I'm not sure. Oh, I see. Here you pushed 4 bytes, right?
Yeah.
Here you pushed 4 bytes. And I wish I had a whiteboard. I think I can do it on this. Let me see if I can write it on this. My poor CS2 class exam. It's a really good question. I think I'd be better off if I could draw it for you. Whatever this is, try someone's test. Hey, what happened to the page of my desk? I don't know. You must perhaps turn it in. Instructors never do that, right? Okay, so here we go. We're going to push, and so I'm not doing a lot of the details. So first we push EAX.
Zoom up.
First we push EAX. Oh, this thing's really. Okay, and this adjusts by 4 bytes. Okay. Now let's push ECX. Doesn't really matter. This is just an example. Another 4 bytes, right? Okay. So far we're good, right? And if you were to get it off the stack, this would actually be +0, right? Because it's right. It's at the very edge of the stack, correct? So right here you can say ESP +0. It's at the edge of the stack, correct? Now you make your call. Here's my function. And the first thing I do is I push EBP. Now, when I push EBP, how many more bytes is the stack adjusted by? Another 4, right? So far, I've adjusted it by 12 bytes. But what did this do? There was a special thing that the CPU did right there, didn't it? Wasn't there a special thing the CPU did when I called? What does the CPU do automatically? We talked about it a couple times. It pushes IP. It pushes the instruction pointer, right? So here, this was adjusted another 4, right? And finally, when I push EBP, it's adjusted by a total of 16. Okay. Now that might be strange. Well, why the heck am I saying +8? What's up with +8? Well, we got the first 4. 0 to 4 is when I pushed EBP. 4 through 7 is the instruction pointer, right? 8 through 11 is the second thing I pushed, and then 12 through 15 is is that first thing I push. So you can just look at the stack pointer and see. So if I had a stack pointer like this, you see that? No, you cannot. Okay, this is the push of EBP, right? That was the last thing I did, correct? This is the instruction pointer. Okay. This is my second parameter. And this is my first parameter. You see how it's always in the reverse order of what we did? And you can just kind of see it as little frames of things I did. So this is ESP sub 0 plus 0, this is ESP plus 4. This is going to be plus 8. This is going to be plus 12. Now, I said we adjusted it by a total of 16, and if you look at it and count all the bytes, it is 16 bytes. Okay? Yes, sir.
This gentleman here asked about the first parameter being passed, and it always repeats. But here we only have 4. I thought when we pushed the first item onto the stack, we always allocated 8 for it.
Yeah, but since we pushed 2 things, it's now 8 and 12. The first one's going to be plus 12.
Plus 12. Okay.
Yeah. Now, if I only push 1, it'd be plus 8. So it's gonna move them out. See, if I pushed 1, it'd be plus 8. If I pushed 2, it'd be plus 8 plus 12. If I pushed 3, it'd be plus 8 plus 12 plus 16. So it's just gonna automatically dynamically adjust depending on how many I push.
So just for like easier thinking, the stack automatically comes with the bottom 2.
No, it was kind of what's trying to go.
The only one that really gets done for you without you having to do anything is this, because when you do a call, but notice here, right here, I pushed EBP, so that's like crap. Don't try this at home. You guys will be laughing. Except for the last test, huh? How dare he take 10 points off? I'll laugh on the class and stuff. Let me get another piece of paper. I wish I had a whiteboard. That would be really very nice. I thought classrooms were supposed to have whiteboards. I have to do that. Let's see. Okay, so let's go through that exercise again. So let's push 3 things now. Push.
You can probably adjust the light on it too, so it's not like that.
That's glaring, isn't it? Kind of like the totally messed up. Is that better?
Yeah, you're right.
So let's push EBX, that's 4. Push ECX, that's 4. Push body dot EAX, that's 4. So now we got 3 parameters we pushed, right? So we'll make our call, my function, down here at my function. Now, so do we have to count this guy? Does he count for how the stack pointer got adjusted?
Yeah.
He
Yeah.
does, right? Because the CPU does something that doesn't tell you it's doing, but you just sort of assume. It's actually pushing IP, right? So this is accounting for another thing, right? So here's my stack, right? Stack is bigger than it has to be. So this was the first one, went there. This is the next one, went there. This is the next one, went there. And as many of these as you push, it's just going to go down, 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 right? The CPU does this for you. That's an automatic. Okay. And the last thing we're gonna do, because we wanna preserve EVP, we push EVP. So the contents of EVP go here. Okay, and so we've adjusted now, because of all the parameters, we've adjusted stack pointer, total of 20 bytes. And it's not always this way, because as I've said, sometimes you're only pushing 16 bits or 2 bytes and doing different things. Okay, so now we want to use EVP. You know how in C++ or C you need a pointer to something? What do you do before you can use a pointer? You have to get the address of the pointer, right? Okay, so that's what we're going to do. So this is analogous to C++ or C. To me, they're the same thing. I know they're not, but it's a simple mind state that way. Okay, so what did I do there? I made, now EVP is a pointer to my data, right? It's just like in C, now I have a pointer into the data. That's what EVP now is. EVP magically transformed into a pointer. So to use it, and I'm not going to be complete here, I'm just going to say EVP plus 8. Always the first parameter on the stack is EVP plus 8. Okay? So that means this is EVP plus 8. EVP plus 12 is here. EVP plus 16 is here. If I push more than that, the stack just goes. Now, what's that expression, stack overflow? What do you think? What do you think a stack overflow is? You run out of room. Is there a possibility you could run out of room? I mean, you guys in CS1, you've done recursion, right? Okay. So with recursion, you can eventually run out of room, can't you? What if you had a bunch of local arrays? I mean, there's a lot of ways to run out of stack space. And normally, the stack is usually initialized to a couple of megabytes, and that sounds like a lot of memory, but you can run out really quick. In fact, I normally in my programming classes, we'll go ahead and go through recursion exercises and overflow the stack just to kind of show them how easy it is to do. It's like super easy. And I taught a language in Haskell. The programming languages class, we use this freaking hateful language called Haskell. And its major control technique is recursion because it doesn't have loops, whiles, fors, doesn't have variables. Pretty bad. Imagine 6 weeks in a language like that. My students were so ready to go on to something else. Okay. So that's kind of my best explanation. Now let me do another one, and just I'll ask you more questions this time. And just based on your feedback, hopefully, I'll kind of get where you get it. Let's go ahead and push 4 parameters here. Let me make my stack. And our stack is big, because we got 2 megabytes of stack. Push EAX. So that's my first right there, right? Push EBX. My next. Push ECX. And as you're doing the push, the stack pointer is automatically moved, just like that. Automatically. It's not like you have to put this on and then add to the stack pointer. It does it automatically. And then we push EDX. And we pushed more on this example than we have in the previous ones. So I'm going to call XYZ, whatever that turns out to be. So this is 4, 4, 4, 4, 4. We'll get to that later. But what happens magically behind the scenes? IP, the instruction pointer gets pushed by the CPU. And they realized that when you made a call, you had to push the instruction pointer so you know where to get back to. So X, Y, Z. So now I want to preserve EBP. And it's kind of like if you don't preserve EBP and someone else is relying on EBP, then his stuff gets messed up, right? So you got to make sure that you're going to preserve EBP. So push EBP. It's another 4. So now the contents of EBP go into there. Okay. Now we got to create the pointer, just like in C. So we're going to create a pointer. Now EBP is our pointer. And that doesn't cost us any stack space, does it? We're not messing up with the stack, we're just doing a simple move. So in order to get this guy here, I just need to do EBP plus 8. That's my pointer in that parameter, right? If I want to access this guy, my pointer is going to be EBP crap. This one. This thing, okay. Second one. You guys are just like that. 12. Then this one is going to be EBP plus 16. And this last one is EBP plus 20, right? So the stack frame that I've consumed so far is 1, 2, 3, 4, 5, 6. 6 times 4, 24. I've consumed 24 bytes, yes.
And why don't you want to just use stack pointer instead of EBP?
Okay, that's a good question. So the answer is, you might want to just use stack pointer, and you could. And if you use the stack pointer, then you would no longer account for that, right? So that's 4 bytes you wouldn't have to account for. Sure. So you could do ESP plus 4, ESP plus 8, ESP plus 12, ESP plus 16. Now, I'm not trying to confuse you, I'm just trying to tell you he's got a valid point. So you could do that. And you have to decide based on what you're doing whether or not you want to do that. But the reason, most of the time I don't, and so I automatically do the move EBP contact ESP. Because let's say I push a register here. Let's say I push EBX. Now I messed it up. ESP now has another 4 bytes, right? And so I might, throughout the course of the function, I might ESP the stack pointer might go all over the place. So what we want to do is we want to make sure that we got something we can count on. EBP is what we count on, because we said EBP, and now we're going to use EBP to access all that stuff in the stack pointer. And that's the reason. But we could do it your way, and we'd be perfectly fine as long as we didn't push and pop in that function. Okay? Now, when we're done, let's say I didn't do that. I still have to pop EBP, right? Now, what would happen if I did a return? Just guess. And I didn't teach this, but just guess. What would happen if I did a return without popping EBP? Right. When it did the return, the CPU is going to pop the next thing on the stack, which would have been EBP. And it's going to go like, who knows? I mean, you don't know. So you always have to make sure that the last thing you do before you perform a ret is that your stack has to be restored to the point where when it does the ret, the next thing it hits off the stack is going to be the instruction pointer. Because if it doesn't, it can go. Now, what do you think hackers do? What do you think hackers would do? Could a hacker potentially use that as an exploit? Yes. The hacker could say, here's a way to get, when he returns from this function, what I'll do is I'll inject something in the wrong place. And the hackers know where IP is in the stack, right? And let's say the hackers wrote this malicious code, and instead of leaving IP where it was, they replaced the value of IP with some malicious function that they wanted to go to. You're screwed, right? It's a very common way for the hackers to get your program to go and do what they want it to do, okay? Those guys are really smart. And there's this thing called process space. A lot of times, even in your browser, have you ever had your browser tell you, you're in a very dangerous site, you really need to get out of there? Even though the browsers are supposed to be safe, these guys, they spend their whole days and nights figuring out ways to do these exploits. And that's one of the exploits that they do, even within the browser, is they'll figure out the address space and then they'll inject that into the stack so that when something does a ret, it's in their code, and they own it. And at that point, they can do anything they want to do. Format your hard drive, your email, your passwords, who knows what. So that's the deal there. Okay.
One question.
Yes.
What is this, what we're doing called?
I'm sorry, what now?
What is the, name for this that we're doing? We're on the push and move and stuff, what is it called?
Well, this is just basic Intel assembly language. Okay. This is kind of the sort of, in C you do the hello world. This is sort of the hello world. Although I think the C hello world is easier than this. Yes. Pardon me? I'd be very glad to.
Actually, can you take a look at number 7? I think there is a mistake in that. Just want to
Remind me.
make sure.
So you want me to do number?
I just want to make sure it's.
Page 3, number 7. Is that what you want me to do? Part 3, number 7.
I'll say,
Okay, so let's see, what are we doing here? Oh, I see.
I think the number 7 might be.
You want me to look at number 7?
Yeah.
So you think I might have made a mistake there? I could have. It'll be the first time.
Actually, I think there are several mistakes, but maybe I'm.
All right, well, let's take a look. I did write an automated program to create this worksheet, so it's possible there's a bug in my program, which is still my fault.
I say.
Okay, 54, 55. Okay, compare ECX to EAX. Jump is less. So it should jump to the second label, right?
Correct.
Okay, so if it jumps to second label, it should put 13 in EAX.
Then on your
That should
answer,
be
you
the
say.
right? Did I have that
Your
one wrong?
Then you say
so
56.
you say EX campaign, not E6. This is from the first one.
Crap.
Yeah.
Okay.
Well, there's several ones like that.
So there are several mistakes, and what I'll do tonight is I'll actually correct these and upload a second version just so that you guys probably have it.
Yeah.
And I definitely apologize for that.
No problem.
Okay, good. Okay, well, thank you very much for pointing that out. Okay, so let's go to the memory thing real quick, if you don't mind. I'll put up a review sheet for the memory, but the main thing about the memory is the speed, and that the closest to the register, to the CPU is the registers. The next closest is the L1 cache, and L1 is maybe a couple of Ks. It's maybe 8 Ks. It's not much. L2 cache is a lot bigger, maybe a couple megs. L1 is caching instructions, and L2 is normally caching data. Okay? And the book even mentioned maybe a third level of cache, which is very unusual. It's going to be on a more expensive system. So I don't think you're going to go to Best Buy and get one with 3 levels of cache. So why do we have cache? Because it's gonna speed things up by significantly. What did we talk about last week, the speed to go to regular memory was gonna be? Anybody recall? It was between 2 and 400 nanoseconds, okay? And the L1 cache is like 5 nanoseconds. Let's see what else we got here.
What was that? Ellen is what?
L1 would be about 5 nanoseconds per. So it'd be like significantly faster than regular RAM. Okay, what's the difference between static and DRAM? DRAM is cheaper and slower, right? Those are the only two things you gotta know for the test. DRAM's cheaper and slower. Okay, let's see, types of memory, okay, blah, blah, blah. Stuff, different flavor. This is basically, okay, what's worse than main memory? Virtual memory, right? Because virtual memory gets swapped out to your hard drive, and your hard drive hard drives of today are pretty fast, but they're still nothing like RAM. We talked about 3 hard drive speeds last week. What were the 3 really common hard drive speeds? 5,400 RPMs, 7,200 RPMs, 10,000 RPMs. The difference between 5,400 and 7,200 is pretty manageable, but then up to 10,000 it's mind-boggling. That's not even a word. It's significantly more expensive when you go up to 10,000 RPMs. My hard drives in my development system are 7,200 just because I cannot justify the extra cost. Let's just look on here. Let me just take a minute and just try to get the difference in prices of. And most of these have different. Oh, nice. 10,000. Okay, let's look at see. Usually they have different varieties with different speeds. Thank you. All right, let's look. 10,000 RPM hard drive. All right, let's just take a look at these prices. So how big is that? That is a 1 terabyte is $214. That's actually not too bad. Okay, Western Digital. And these are all, that's actually really not bad. So I take my words back. If that's the price they were now, I would buy them. Before, when I was outfitting my development computer, they were like $500. That's actually very, very reasonable.
Yeah, because of the solid state drive now.
I'm sorry, what now?
Because of the newer generation solid state drive.
Yeah, I'm just one of those old farts who just use regular hard drive, I guess. But that must be why they're so much cheaper, because the solid state drives they're really coming down in price. Let's see what those are going to cost us now. Solid state.
SD.
I'm sorry, what now?
It usually goes by SSD.
SSD. Like that?
Yeah.
Okay. All right, so let's get a decent size. Let's see. These are still pretty small. Okay, this is fairly big. So 1 terabyte. That's less than 10,000 RPMs was 3 years ago. So this is going to turn out to be really fast. And I mean, if I was looking for extra space, I would seriously consider that. Let's see what the you see the access. Okay, so reads are 540 milliseconds.
Megabytes.
That's pretty fast. Okay, so that was a nice excursion. And 25% of your test will be memory. I'm not going to ask you a bunch of questions. And I may just make them multiple choice. Would you rather have multiple choice?
Yes, yes.
Okay.
Thank you.
You don't like true false, do you?
No.
Those are bad because you have to, sometimes you don't know you only have 50-50 chance.
More than true or false, open-ended question, I hate those
Like the plague, huh? I don't think you're going to get any on this test. Okay, let's see. Cache memory. I think we've already been over this. Trying to think. Okay, so what's that kind of, what happens to memory and cache when it's no longer needed? It's evicted, right? We talked about evicted. There's a victim block. That's about all you're gonna have to know as far as like getting rid of cache. What are the ways that you can think of to decide? How does operating system decide what cache items stay in cache?
Based on algorithm.
Based on an algorithm that factors in the number of times it's used and the time since the last time it was used. So I think that's probably it for here. Okay, so we'll do 6 questions similar to review sheet 1, 6 questions similar to review sheet 2, 6 questions similar to review sheet 3, and then 6 multiple choice questions on memory. Fair enough?
Yeah.
Be glad to. Okay, I think I got distracted because there's a mistake. Hopefully,
Well, that's not all of it. We could just do like one.
let's do a few of these, and if there's a mistake, we'll figure it out. Okay. Okay. So EDX is 26 EAX. So jump if EDX is greater than EAX. So this should be false, right? A false test. So it should fall through to first label. It should move 4 into EAX and jump to third label. So the answer should be EAX is 4. Ah, we got that. I got that right.
The first sets were fine.
That's all you have to write.
Oh, okay.
I'll put a blank for you too. I'll say EAX equals blank.
Okay.
Yes. I'm sorry, what?
JG, what was that?
Jump if greater. So there are only going to be 4 of these I'm going to ask you. Jump if greater, JG. Jump if less, JL. JE, jump if equal. And JNE, jump if not equal. Now there are 2 others I would like to ask you, but I'm not going to. Is jump if less than or equal to, jump if greater than or equal to. I'm not going to ask those because if you can do JG, you can do JGE, right? So I won't ask you JGE or JL. Now, there are a bunch more, but we don't need those for right now. Right now, I just want you guys to understand how it kind of works, okay? All right. Let's do another one. And by the way, I'll make sure I check my email a lot in the next couple of days if you have questions. And I have office hours tomorrow from 1 to 4. Help yourself. Okay, EBX is 1, EAX is 42. Compare EBX to EAX, jump if greater. Is it greater? No.
Oh.
So this should fail. This should be a false, right? So it should fall through to here. Now it jumps to third label. So what was that, 35? Okay, that's correct. Okay? And here again, you're not going to have to write all this crap. Yeah, I know that's the answer. I just wanted to try to explain it as best as I could. On the test, it'll be like this. EAX equals, and that's all you have to do. Okay? Isn't that easy? I'm trying to atone for the last test. All right. See you guys. Yes. That what?